The saxophone is considered either an open pipe or an open-closed pipe because technically both ends of the saxophone are open, but since the mouthpiece is so much smaller, it is rendered insignificant and therefore acts as a closed end, aka an open-closed pipe.
A tone is made from regular, evenly spaced waves of air molecules. Tones sound different because of the pitch, which is caused by different spacing in the waves. The closer the waves are to each other, the higher the tone sounds.
Now, the alto saxophone is in concert pitch E-flat. This pitch is meant so that two different instruments, for instance the clarinet, which is in concert pitch B-flat, may play two different notes but the same pitch. This means that the saxophone is a transposing instrument.
The vibration of the reed creates the sound in a saxophone. The vibrations create the sound waves that travel down the pipe or instrument. The frequency changes by opening and closing various keys on the saxophone. The more keys left open, the shorter the pipe is. Therefore, the pressure node moves up the saxophone from the end. The more openings, the higher the pitch.
So every time I lifted up a finger and a key was released, my pitch went higher. And every time I pushed my key down, my pitch went lower.
Another way to lower or raise the pitch is by pushing in the mouthpiece or pulling out the mouthpiece. By pulling out the mouthpiece, you're making the pitch lower because the pipe is longer. By pushing in the mouthpiece, you're making the pipe shorter so the pitch raises.
The octave key is a lot like the straw experiment we did earlier in the year. In a sense, the key cuts off the length of the instrument the same way we cut the straw. Every time you push down another button on the instrument, the pitch lowers.
On the saxophone, there are many different ways to play the same note. For example, B-flat has 3 different fingerings. So no matter which variation of the key I push, I always get the same pitch and same frequency. So when I push down these 2 small keys with my left index finger, I get. But when I push down my index finger on my left hand and my index finger on my right hand, I get. And then, also, when I push down these 2 fingers down and I use my right hand to push down the bottom side key on my instrument, I get. So, it's. Which is all the same note, even though they have different keys that are being pushed down.
Temperature affects the speed of sound because the warmer the air temperature, the more the air molecules can vibrate, so sound waves can travel faster. All sound waves travel at the speed of sound. Assuming the speed of sound is constant, the wavelength changes the frequency. If the wavelength is longer, then you won't hear them as often. Thus, the frequency is lower than that of shorter waves.
To demonstrate this concept, I will play in 2 different environments. I will use this tuner to measure what frequency I'm playing at. When the light is green, I am playing at 440 Hertz.
Okay, it's 75 degrees in this room, and I'll be playing a concert B-flat pitch. Okay, it's 85 degrees, and I have not moved my mouthpiece since I played exactly 440 Hertz inside at 75 degrees.
Now notice, when I was inside at 75 degrees, I was exactly at 440 Hertz. But when I went outside, where it was 10 degrees warmer, I was 12 cents above that, making me above 440 Hertz.
The shape of a room affects sound. When a sound reflects off a parabolic surface, it bounces off in a straight path. This is why concert halls are designed with a parabolic shape. The sound goes directly to the audience instead of bouncing around on stage.
Although the person recording this is sitting behind the band, he is still able to hear the performer as well as he would have if he sat in the audience. This is due to the parabolic nature of the concert hall.